Imagine cracking complex problems thought to be unsolvable by even the most powerful computers. That's the tantalizing promise of a new quantum algorithm called Decoded Quantum Interferometry, DQI. While quantum computers haven't yet delivered on their full potential, DQI offers a fresh approach to tackling optimization challenges. But here's a crucial point. Achieving a true quantum advantage, a problem solvable only by a quantum computer in a reasonable time, remains a monumental hurdle. NP-hardness results basically tell us that for many optimization problems, finding the absolute best solution, or even a pretty good one, is likely impossible for any algorithm, be it classical or quantum, that runs in polynomial time, that is, a reasonable amount of time. Think of it like trying to find the highest peak in the Himalayas while blindfolded. It's just too complex to do efficiently. However, some problems have a significant gap between how well classical algorithms can approximate the solution and the theoretical limits of how bad an approximation could be. A prime example is the closest vector problem. And this is the part most people miss. This gap presents a window of opportunity for quantum computers. The goal: to find an approximation in polynomial time that would take classical algorithms an astronomically long, superpolynomial, time to achieve. It's like finding a significantly higher peak in the Himalayas than anyone else can, even with better maps and equipment, but without having to search every inch of the mountain range. Over the last 3 decades, quantum algorithms for optimization have been a hot topic, with researchers exploring potential superpolynomial speedups for specific optimization problems. However, discovering a definitive superpolynomial quantum advantage for optimization is incredibly difficult and largely unsolved. We're still searching for that killer app that showcases the true power of quantum computation in this domain. DQI leverages interference patterns to guide the optimization process. It uses a quantum Fourier transform, QFT, to make amplitudes constructively interfere for symbol strings with high objective values. Think of it like focusing a beam of light to amplify the signal of the best solutions, making them easier to find upon measurement. This is a departure from many earlier quantum optimization methods, which are Hamiltonian-based. Hamiltonian-based approaches are often seen as exploiting the local structure of the optimization landscape, like tunneling through barriers. But DQI leverages the sparsity often found in the Fourier spectrum of objective functions for combinatorial optimization problems. It's like finding hidden patterns in the data that point towards the optimal solution. Chen, Liu, and Zandri's work on finding short lattice vectors, which uses Fourier transforms, can be seen as a precursor to DQI. But whereas Hamiltonian-based quantum optimization methods are often regarded as exploiting the local structure of the optimization landscape, for example, tunneling across barriers, DQI instead exploits the sparsity that is routinely present in the Fourier spectrum of the objective functions for combinatorial optimization problems. Before diving into how DQI outperforms classical algorithms, let's illustrate its essence with the Max-XORSAT problem. While not DQI's biggest success story, Max-XORSAT offers the simplest explanation. Max-XORSAT involves finding an n-bit string that satisfies as many as possible of m linear mod 2 equations. Imagine you have a system of equations where the variables can only be 0 or 1, and you want to find the combination that satisfies the most equations. We can rephrase this as maximizing the objective function f(x), which represents the number of satisfied equations minus the number of unsatisfied ones. The Hadamard transform of f reveals a sparse structure with only m non-zero amplitudes. This makes preparing the state sigma f(x) relatively easy. Measuring this state yields a bias sample, slightly increasing the likelihood of finding strings with high objective values compared to random sampling. But here's where it gets controversial. The Hadamard transform of f is extremely sparse. It has m non-zero amplitudes, which are on the strings b1, bm. Some may argue that this sparsity is not always present in real-world optimization problems, limiting the applicability of DQI. What are your thoughts? To boost this enhancement, DQI prepares states of the form p f equals sigma p f x x, where p is a carefully chosen polynomial. The Hadamard transform of this state takes a specific form involving coefficients w0, w, and Hamming weights. The DQI algorithm prepares p f in 5 steps, preparing a superposition over Dick states, imposing a phase, computing a matrix multiplication, uncomputing, and applying a Hadamard transform. Uncomputation, where the intermediate result is undone to free up qubits, is crucial in quantum algorithms. However, uncomputing y in the fourth step isn't straightforward because the matrix B isn't square. Inferring y from BT becomes an underdetermined linear algebra problem. But we also know that the Hamming weight of y is limited. This transforms the problem into syndrome decoding for a classical error-correcting code, which can be NP-hard in general. However, when B is sparse or has specific algebraic structures, the decoding problem can be solved efficiently even with a large number of errors. By using a reversible implementation of such a classical decoder, we can uncompute y. Approximate solutions are obtained by measuring P(f). A higher degree polynomial in P(f) biases the measured bit strings towards solutions with high objective values, but it also requires solving a harder decoding problem. Therefore, the key to DQI's power lies in carefully selecting the polynomial P and a suitable decoder. While DQI has broader applicability, the most general optimization problem we apply it to is Max-LINSAT. Max-LINSAT involves finding a string that satisfies as many constraints as possible, where each constraint is defined by a subset of a finite field. Max-XORSAT is a special case of Max-LINSAT. Consider a Max-LINSAT instance where each set has size r. If we can correct up to bit flip errors on codewords from a specific code in polynomial time, then DQI achieves a certain approximate optimum to the Max-LINSAT problem, as described by a formula that resembles a semicircle. This formula is often referred to as the semicircle law. From this semicircle law, any result on decoding a class of linear codes translates directly into a result regarding the performance of DQI for solving a class of combinatorial optimization problems that are dual to these codes. This opens up two avenues for research, leveraging existing coding theory results to guarantee DQI's performance, and using computer experiments to compare the empirical performance of classical heuristic decoders against classical heuristic optimizers. DQI can then be benchmarked against classical heuristics, even for problems too large for current quantum hardware. We first use rigorous decoding guarantees to analyze DQI's performance on the optimal polynomial intersection, OPI problem. OPI involves finding a polynomial that intersects as many subsets of a finite field as possible. In essence, we're searching for a curve that passes through as many target zones as possible. OPI is a special case of Max-LINSAT where the matrix B is a Vandermonde matrix, making the code a Reed-Solomon code. Syndrome decoding for Reed-Solomon codes can be solved efficiently using the Berlekamp-Massey algorithm. This allows us to set a high error correction limit in DQI. OPI has been studied under different names in coding theory and cryptography. It can also be viewed as a generalization of the polynomial approximation problem. We find that, for the parameter regime addressed by DQI, the best approximation achieved classically in polynomial time is 1 divided by 2 plus n divided by 2p using Prang's algorithm. However, DQI with the Berlekamp-Massey decoder exceeds this satisfaction fraction in the limit of large p. Classically, exceeding Prang's algorithm requires brute force search or slight modifications, which are exponentially slow. Thus, DQI achieves a superpolynomial speedup for this problem, assuming no polynomial time algorithm can match DQI's satisfaction fraction. At present, there are no direct results showing that the OPI problem in the parameter regime we consider is classically intractable under standard assumptions. However, such results exist for certain limiting cases, and we propose extending these results to regimes more relevant to DQI. As a concrete example, for n is almost equal to p/10, and r/p is almost equal to 1/2, DQI achieves a significantly higher satisfaction fraction than Prang's algorithm. We challenge the algorithms community to beat this with a classical polynomial time algorithm. Isn't it fascinating that solutions expected to exist remain elusive for both quantum and classical algorithms? To find classically intractable instances of OPI solvable by DQI with minimal quantum resources, we find it advantageous to choose n/p is almost equal to, r/p is almost equal to 1/2. For these parameters, DQI achieves a high satisfaction fraction. Achieving this classically has a prohibitive computational cost. The dominant cost in